Good afternoon, since it's past noon. It is a real pleasure today to be welcoming Professor Joan Brennecke. She is the Keating Crawford Professor of Chemical and Biomolecular Engineering at the University of Notre Dame. She is a chemical engineer. All her degrees are in that area. The first degree from the University of Texas at Austin, followed by a master's and PhD from the University of Illinois. She has been at the University of Notre Dame throughout her career as a faculty member. She's recognized as one of the real-world leaders in the area of green solvents, particularly supercritical fluids and ionic liquids, and has received a very large number of honors and awards for her work over the years. I'll just mention a few. She is the recipient of the Ipariev Prize and several other awards, the Murphy Award and the Stiglitz Award from the American Chemical Society. She received the Professional Progress Award from the American Institute of Chemical Engineers. She received a large Department of Energy prize that I don't remember the name of. She's the editor, the Lawrence Prize, thank you. She's the editor of the Journal of Chemical Engineering Data, a very important American Chemical Society journal. She also received the John Prausnitz Award in Applied Chemical Thermodynamics and was elected to the National Academy of Engineering in 2012. She will be presenting today her work on ionic liquids for post-combustion carbon dioxide capture. John?
All right, well, thank you very much, Thanos, for the lovely introduction. It's a great pleasure to be here to talk with you in the Andlinger Center about some of our work on CO2 capture using ionic liquids. Just as an outline of my presentation, I will give a little bit of background and first start talking about the physical solubilities of gases in ionic liquids. And then I'll move on to what we came to find to be important for using them for post-combustion CO2 capture, which was incorporating chemical complexation into the ionic liquids where they could react with CO2. And I'll try to point out some of the things that we think are important advances that we've made in developing these materials, in doubling the CO2 capacity, eliminating a viscosity increase, being able to tune the reaction enthalpy, and then I'll also give you some details on the reaction chemistry that we have found to be important. And then I will finish up with kind of an offshoot of this work where we've developed some materials that we call phase change ionic liquids. So I'll describe that when I get to that point. So I assume that most of you are familiar with ionic liquids. Ionic liquids are simply salts with low melting points. They are not like simple sodium chloride and so on, in that we have to incorporate things into them that frustrate their packing so that this will lower the melting point. It turns out that you can make low melting salts, salts without any water present or other solvents, from all kinds of different cations and anions. So this becomes a great design opportunity because we can make them have very different properties, very different physical properties, very different phase behavior properties with other things, so very different chemical properties, electrochemical properties as well. And so here's just a list of some of the things that people will use for the cations. Much of the literature focuses on these imidazolium cations, but that's just a kind of a me too sort of thing. You can have simple anions like halides or much more complicated things. So there's a great deal of design opportunity. The reason why they first got attention and continue to get a lot of attention is that because they're salts, they have very, very low vapor pressures. The Coulombic forces means they don't want to evaporate. And in fact, the vapor pressures can be, less than 10 to the minus 8 bar at ambient conditions or even 100 degrees centigrade or so. So they really are very, very low volatility. And as I said, they're very different than things like sodium chloride. So these imidazolium things, you always put a symmetry into them. We wouldn't, methyl creates higher melting points, so we put a symmetry. And if we can do that in the cation and the anion, we can get very nice low melting salts. So my research group, I am basically an experimental thermodynamicist. Our interests are really in phase behavior and thermophysical properties. So in my research group, we design, synthesize, and purify all kinds of new ionic liquids. You, of course, now can buy very conventional ones from various suppliers. We usually are not interested in those because we're trying to design them for particular applications. So we do most of the synthesis ourselves. As I said, we're interested in thermophysical properties and characterizing these materials with things as simple as melting points and decomposition temperatures, and viscosities, densities, ionic conductivities, and so on, excess enthalpies when we mix them with other things or with other ionic liquids, and very much interested in phase behavior. And here I'll be talking about gas solubilities, but we also are interested in other types of vapor-liquid equilibrium, liquid-liquid equilibrium, solid-liquid equilibrium, and all combinations thereof. I mentioned that we're interested in electrochemical properties because these ionic liquids can be used as electrolytes in a variety of applications. So we care about electrochemical windows. We've done some work on electrochemical reduction of carbon dioxide as well as electroplating. I'm not really a reaction engineering kind of person, but we do have to worry about reaction chemistry, especially when we've been designing the ionic liquids to react with CO2. And then in my group, we do some thermodynamic modeling, but macroscopic thermodynamic modeling. I've done most of my collaborations with other people to do the molecular simulations. So what I care about is the possible use of ionic liquids for a wide variety of energy applications. And so I've listed just some of the potential energy-related applications on this slide. We are particularly interested in using them for separations. So all types of gas separations, the one of which I will be talking about today is the post-combustion CO2 capture. But we've also looked at using them to break azeotropes, to extract organics from fermentation broths, so a wide variety of separation applications. We've also done a fair amount of work in using them for heating and cooling applications. So we had a large ARPA-E project to use CO2 ionic liquid systems for co-fluid vapor compression refrigeration. We've also looked at them for more conventional absorptive cooling applications. And then, as I already mentioned, we care here, and here our interests are much more fundamental interests, but the use of ionic liquids as electrolytes. And people have looked at them for batteries, supercapacitors, fuel cells, dye-sensitized solar cells, and many other things. So these are sort of the three areas where my research group has focused our attention. I should mention there's lots of other energy-related applications that people have used ionic liquids for, or investigated them for. There's huge efforts in biomass processing because you can dissolve cellulose and all kinds of other biomass components in some of the ionic liquids and then have opportunities to process them in single phase. There's also been interest in using them as heat transfer fluids and many, many other things. So that was just to give you a little example of sort of the scope of where I see some of the applications of the things that I'm interested in of ionic liquids for energy. So, all right, so now to focus on the CO2 capture. Obviously, there's many important CO2 separations. Commercially, CO2 from natural gas, CO2 from air is not one of my favorite things, but some people care about that. Separating CO2 from pre-combustion gases like you would have in IGCC, but also whether we could remove CO2 from post-combustion flue gas. And as you all know, a large fraction of our energy still comes from fossil fuels, and worldwide that certainly will continue to be the case for some time. And something like 50% of the electricity in the US is actually generated from combustion of coal, and of course more from natural gas. And these point sources, like these power plants, are good targets for CO2 capture. But the challenge is that we need an alternative to the aqueous amine technology. We need something that requires lower energy because estimates are that aqueous amines the parasitic energy load would be something like 28%. So 28% of the power generated by the power plant would have to be used in the separation process. And so that's very prohibitive. Aqueous amines also have some other problems, corrosivity, side reactions, degradation at lower temperatures, and so on. So this is why we and many others have been looking to develop alternative technologies for CO2 capture from post-combustion flue gas. And the one we're focusing on is the ionic liquids. And I guess I don't need to actually walk back over there. So, all right, wrong way. Okay, so we are thinking about this because we have a liquid. We're thinking about this as the same type of process as we would have with aqueous amines. So we would have our flue gas from our power plant coming out at atmospheric pressure. For coal, it's about 12% CO2, and we would want to contact it with our absorbent and in some kind of absorber column. And then we would want to regenerate our ionic liquid absorbent, so we would want to remove the CO2 so that we could reuse the ionic liquid. So we first got the idea of this many, many years ago. So 15 years ago was when we first started working with ionic liquids. At the time, most of the work was being done in chemistry departments where people were using them as alternative solvents for all kinds of different reactions. And I was at a conference and I heard someone talking about ionic liquids, and I was sitting there in the conference with Eric Beckman from the University of Pittsburgh. We were both there presenting our work on supercritical CO2. And we saw this presentation on ionic liquids and said, gee, either this is crazy or this may be very interesting, and we should do something with ionic liquids in supercritical CO2. So I read a few papers and found out that people were saying, oh, I'm being so green by using this low volatility solvent for my reaction, but then they would use diethyl ether to extract their product out of the reaction mixture. And I said, okay, that's kind of silly. Why don't we use our supercritical CO2 to extract something out of an ionic liquid? And that is what we ended up doing. But of course, we had to understand the phase behavior. And so we looked at the phase behavior. And you can see here we're looking at very high pressures because I was interested in supercritical CO2 at the time. And we just picked this ionic liquid. At the time, you couldn't buy anything. So Eric Beckman actually had his graduate student make it, and I must say very badly. But nonetheless, it was mostly this. And and so we looked at what happened when we put this in contact with CO2. And what we found was an awful lot of CO2 dissolved in the ionic liquid-liquid phase, but we couldn't detect any of the ionic liquid in the CO2 phase. And that's very nice, even when we got to relatively high pressures. And that, you know, you don't really think a salt's going to dissolve in a non-polar fluid. And so that sort of made sense. And we recognized this was very, very interesting. But this high solubility, physical solubility of CO2 in the ionic liquid is what got us thinking about the potential of using it for gas separations. So we needed to look at solubilities at somewhat lower pressures. And so here's an example. This is the solubility of CO2. I've got mole fraction of CO2 as a function of pressure at various different temperatures. And this is one of these imidazolium ionic liquids with this bis-trifluoromethyl sulfonamide anion. And so obviously, as we increase the pressure, the solubility increases, and as we increase the temperature, the solubility decreases. So then we looked at, well, what's the solubility of other gases? This is a very slightly different ionic liquid, same anion, but here now instead of an imidazolium cation, I have a pyridinium cation. The solubility of CO2 in this guy is about the same as the one on the previous graph, but then we got the solubility of some other gases. So ethylene and ethane, and then down here is methane and oxygen and nitrogen. So this difference in the solubilities is what really got us interested in using them for the possibility of gas separation. So we did a lot of work. on the physical dissolution of gases in ionic liquids. And what we found is that for CO2, the enthalpy of dissolution is about minus 12 kilojoules per mole. And I can't change that very much for the physical dissolution. It's about minus 11, minus 12, minus 13, something like that. All right? And that's nice, because that means when I do the regeneration, I wouldn't have to have very much heat to remove the CO2. But the problem is that the capacities are way too low if I want to use this for post-combustion flue gas. So I would need a huge amount of ionic liquid, and when we did some preliminary process modeling, we said from that initial work that we saw with the imidazolium PF6, we would have to increase the capacity by about 10 times to make it competitive with the aqueous amine solutions. So obviously what we need to do is put some chemical complexation in there so I can get much higher capacities at the lower partial pressures of CO2. But I really would like to make that not too weak of a chemical complexation because I want to keep my regeneration energies down. So we were actually not the first people to think about this. The first person to do this was Jim Davis at the University of South Alabama. And what he did was he tethered an amine to the imidazolium cation, and he bubbled CO2 through it. And he was just weighing the sample. And he saw that the mass increased, and that corresponded to something close to 1/2 mole of CO2 per mole of ionic liquid. And so he concluded that the chemistry of the reaction was the same as it is with aqueous amines, where the CO2 first reacts with the first amine and then reacts with the second, does the deprotonation, so you get this 2-to-1 chemistry. Right, 2 amines with 1 CO2. And if you read his paper carefully, there's one little comment in there that says, oh, and by the way, when we bubbled the CO2 through, the viscosity got really bad. Okay? All right. So my colleague, Bill Schneider, started asking the question, can we do better than this? And we were particularly interested in this capacity issue. So he did some simple DFT, or his graduate student did some simple DFT calculations. In the first case, he tethered the amine to, actually in this case, a pyridinium cation, and compared the energetics for the first addition of CO2 and then the deprotonation, compared it to monoethanolamine, where we know we get the 2-to-1 chemistry. All right? And what he found was that the first reaction with CO2 was similar to what we have for monoethanolamine, but that the second step was actually very downhill compared to monoethanolamine. So this confirms why you would have the same chemistry of, with the monoethanolamines as when you tether the amine to the cation. But then he tethered the amine to the anion. And what he found was a little bit more favorable for the first addition of CO2, but the deprotonation to form the dianion is very much uphill. So his prediction to us was that if we stuck the amine on the anion, I should get 1-to-1 chemistry. So I should get 1-to-1 uptake. So what we did was we made a bunch of amino acid-based ionic liquids. And so here's 2 examples. This is proline, so it's a prolinate anion. This is methionate. And we paired these, for no particular reason, with this tetraalkyl phosphonium cation. Okay, there's a reason it's available commercially. Okay, and so pretty long chain tetraalkyl phosphonium cation. And so you can see that we certainly get reaction with CO2. We get near 1-to-1 uptake at incredibly low partial pressures. So I've now changed this to not mole fraction, but moles of CO2 per mole of ionic liquid. And once again, very low partial pressures. But incidentally, when the CO2 reacted with these ionic liquids, we saw a very large increase in viscosity. And in fact, this shows you how bad it was. So here's a couple examples. So it's green to green, blue to blue. So almost 2 orders of magnitude increase in viscosity when these ionic liquids were fully reacted with CO2. Now, I mean, I don't know about you, but I can't really deal with this, right? I can't really think about how to deal with this in an industrial process. But my student did recognize that there was one on this graph that wasn't as bad, and that was the prolinate. So the prolinate is the kind of gold to red. And so the prolinate's increase in viscosity when fully reacted up with CO2 was only about an increase of about a factor of 5. And so the question then is, well, what's going on here? And so you can get a guess at what's happening just by looking at our series of who was worst and who was least bad in their increase in viscosity when complexing with CO2, is that clearly we've got some hydrogen bonding going on. And this was confirmed by my colleague, Ed McGinn, looking at one of these systems where the amine was tethered to the cation. But sure enough, in their molecular simulations, they saw the formation, the pervasive formation of this hydrogen bonding. So we're basically making a polymer. And in the prolinate, we're just cutting down on our opportunities for hydrogen bonding. So if we want to eliminate this big viscosity increase with reaction when it reacts with CO2, we need to cut down on those opportunities for hydrogen bonding. And so this is when we moved to a new class of ionic liquids that we came up with, which we call AHA ionic liquids. So, and that was not my idea, I want you to know. That was one of my clever colleagues. And so we're trying to get rid of protons, all right? And so they're essentially aprotic heterocyclic anions. So they're things like, shown here is a perolide, and this is a pyrazolide. So here's these guys. This is a sinyl perolide. This is trifluoromethylpyrazolide. And here are their uptake curves. Once again, my nice low pressures, moles of CO2 per mole of ionic liquid. So they pick up a fair amount of CO2 at relatively low pressures, but what's more important is their viscosities essentially do not change when they're reacted or when they're not reacted with CO2. So we were pretty happy with this, and we can then calculate our reaction enthalpies by doing the uptake curves at multiple different temperatures. Here we model this as some physical absorption, but then the CO2 reacting with the IL to form this complex with the anion. So we fit these and get our equilibrium constants as a function of temperature, and from that we can get our enthalpies. The physical part's the same as always. In this case, the chemical reaction is about minus 43, 44 kilojoules per mole. We also have measured, we have also measured these by calorimetry, and our calorimetric measurements are consistent with what we get from the Van Hoff equation. So we've gone on to look at a wide variety of different motifs. Like I mentioned, the perolides, the pyrazolides, but also imidazolides, triazolides, tetrazolides are too weak. All right, but we certainly have made those as well. And here's just an example of a series of different types from the categories that I showed on the previous slide. And these are the uptakes as a function of pressure at room temperature. And so the guys that have relatively small uptake are relatively weakly reacting with CO2, and the ones that are much steeper are the ones that have the more larger negative delta H's of reactions. From process modeling, it seems like this minus 50 to minus 55 kilojoules per mole is about the optimum to minimize the energy use in the entire process. So we're able to tune those reaction enthalpies in ways to get the appropriate materials for the CO2 capture application. So I should say that in doing this, we came upon life being a little bit messier than we would have liked it to be. And that is that this is the reaction that we want to happen. We want the CO2 to react with the amine on the anion to make this carbamic acid. So what we found when we used these Phosphonium cations is that we also had Phosphonium Ylide formation. I see a nod or two. All right, and we probably should have expected this, that the alpha proton on the phosphoniums is rather acidic, and so our anion can pull that guy off, and then this can react with CO2 as well. And turns out we discovered this by trying to measure the reaction kinetics, because we expected our activation energies for the reaction to be rather low. And for some of them, as we did this at different temperatures, the activation energies were too high. And that got us suspicious, and we started looking at things more carefully. So we actually have two reactions going on in parallel. The one that we anticipated, and then this Ylide formation and its reaction with CO2. And we've investigated this by a wide variety of different techniques. What I'm showing you here is the FTIR. And you can see that at higher temperatures, as we raise the temperature, we get the formation of an additional peak down here. And this is the one that we attribute to the CO2 that is reacted with the cation. Both of the reactions turn out to appear to be fully reversible. So if we bubble through with nitrogen or we pull a vacuum on our sample, we get both the reaction of the CO2 with the anion to go back to baseline, as well as this reaction with the cation. Although this one is a little harder, so we don't know what the delta H of reaction is, but we anticipate it's a larger negative number. Yeah?
The presence of water vapor change the behavior?
Oh, it's a whole nother talk. All right. All right. So I have not included any of the work that we've done here on trying to understand what the effect of water is. So there's many different effects. The main one that we have to worry about is water reprotonating the anion in the presence of CO2. Without CO2, that does not happen. But when we have CO2 present, so we've got an acid present, then we get some reprotonation of some of these aprotic heterocyclic ionic liquids. And so we're working on quantifying that at the moment. So that is a very important issue, to be able to choose the ones that do not reprotonate, right? There's other things that go into it. The viscosity, I showed you when we react them up with CO2, the viscosity does not increase. But if you have just a little bit of water in there, then it does. Because tell me why? Hydrogen bonding, right? The water is providing the hydrogen bonding bridge. Of course, if you put a little bit more water in there, then the water, of course, has low viscosity, and so then it does its dilution thing, and the viscosity goes down. So it's when you have about a 1-to-1, it's a little less than 1-to-1 of water to the ionic liquid that you get this little increase of about 2- or 3-fold in the viscosity before it starts going down. Yeah? Now that he started this.
So in batteries, a little bit of water has tricked a lot of people into thinking that the viscosity is lower with certain, and now there's yet another component. There's an extra cation in the form of lithium salt. So when you first showed that increase, I was wondering if just parts per million water would decrease.
No.
But I guess
right.
you said it actually.
Well, for this reaction with CO2, where it can provide the hydrogen bonding bridge, like I said, it actually increases at first and then decreases a bit. We're incredibly careful. We always measure water content of everything because water does make a big difference.
And so just to make it more complicated, if you have another cation like lithium or sodium, does that counteract that effect, or at least
counteract the effect? Well, when we add lithium salts to the ionic liquids, the viscosities go up.
Right. But then
Right, so when we don't have this CO2 reaction thing, when we're just doing ionic liquid lithium salt mixtures, then adding a little bit of water massively decreases the viscosity. So you always have to measure the water content. And so for the typical ionic liquids that people are using for electrolytes, you can get them down to about a few tens of parts per million of water pretty easily. Some other anions, some of these are a bit more hydrophilic, and so a few hundred ppm of water is what we aim for. So thanks, yes, but water is a big issue. So, okay, so all I was trying to say here is that from the uptakes and from the IR, they look to be reversible, but at least I always say on the time scale of our experiments, because in the this thing here, we are making neutral cyanoperol, which can vaporize. Of course, it has a very high boiling point, and I suspect its activity coefficient in the ionic liquid is very low. So it doesn't like to leave the ionic liquid. So I suspect that's why we see this nice reversibility. So our favorite is phosphorus NMR. So here it is, pure. We just got one peak, and you're supposed to ignore this because this comes from the manufacturer of the Phosphonium to start with, and it's always there. Okay, so one peak, and after we react it with CO2 at the higher temperatures, then we get this additional peak. So you can see, in this case, as much as 11–12% of what's happening is the cation reaction with the CO2. And so these do correspond very nicely. There's very little there. This is at 40 degrees, very little there. At 60 degrees, then we've got the more of it there. So we've also looked at this with 2D NMR to convince ourselves, and this is with C13 labeled CO2, to convince ourselves that it is the CO2 that is reacting with the cation, and convinced ourselves from the 2D NMR. Sorry, and if someone likes mass spec, there it is. It's there, okay? So now we can eliminate this by using a different cation. So a very simple change would be to go to, instead of phosphonium cations, to go to ammonium cations. And because the ammonium Ylide is much less stable. And sure enough, when we make ammonium-based cation ionic liquids with the same anions, we see much less formation of this species that has reacted with the cation. So we can eliminate that. There's always trade-offs in life. We love phosphoniums because they have much higher thermal stability. The ammoniums with the same things have maybe a 50 to 100 degree lower thermal decomposition temperature. All right, so to go back to the kind of the main story here is that I've shown you a lot of things with this tetraalkylphosphonium cation with the long alkyl chains. Well, those things are too viscous. So we need to lower the viscosity. So here's just an example with this cyanoperolide anion where we just changed the length of the alkyl components on the tetraalkylphosphonium from the big long floppy guy to short guy. And you can see that we get almost a 10-fold decrease in the viscosity simply by adjusting those van der Waals interactions that come from the length of the alkyl chains. Interestingly, the CO2 uptake actually changes a bit. And so here is the room temperature uptake. So this is where we don't have any interference from this cation reaction. So we go from the blue, which is our big long floppy chain guy, to triethylbutyl, all right, so the much shorter chain, and our uptake at low partial pressures is actually greater. So this got us to ask the question is, why do these alkyl chains on the cation affect the uptake? And so what we believe is the case, and we've looked at conductivities and all kinds of other different measurements to convince ourselves that this is true, is that we don't really expect much of a change in the delta H of reaction of the anion with the CO2. I told you with the cyanoperolide, it's this minus 43, 44, 45 kilojoules per mole. So what we think is happening with these different length alkyl chains, we're changing delta S, right? So we're changing the entropy So the reordering that has to occur when the cation alkyl chains that are surrounding the anion have to move to let the CO2 in to do the reaction with the anion. So we believe that this is a change in delta S, and it doesn't take much of a change of delta S to explain this change in the uptake. All right, so then I said I want to tell you a little bit of a kind of an offshoot story, which is what we call phase change ionic liquids. So what happened is that we were messing around with these different alkyl chains, and so we made some of these tetrabutyl Phosphonium AHAs ionic liquids, and they were solids, and at room temperature, and so so we measure the melting point. I don't know, the melting point was 45, 50 degrees, something like that. And so I said, well, that's fine. Go ahead and heat them up to where they're a liquid and measure the CO2 uptake at 60 or 50 or whatever, okay, where they're liquid. And so my student very happily did this. So he measured the CO2 uptake at 60 degrees, and so he did the measurements, and he left the 1 bar of CO2 pressure on the instrument and turned the temperature controller off and went home. All right? And he came back in the next morning, and he expected it to have resolidified. So he expected to see a solid in the bottom of the flask, and it was liquid. All right? So he was very clever enough to realize that this is very interesting and rushed in to tell me about it, at which point we realized that this could work to our advantage. So it means that the melting point of the complex is lower than the melting point of the original material. And so we could envision a process that might substantially reduce the energy consumption of the capture process because of this change in phase, taking advantage of the heat of fusion. So our idea then is that we would have the flue gas going in, contacting the solid material, so it's a solid, but then as it reacts with CO2, we would have a liquid coming out the bottom, the complex. We could then run that through our desorber regenerator, a spray dryer, where we would remove the CO2 and we'd go back and make our solid. Now, the benefit of this is that in the absorber, you're having stuff go from solid to liquid, so you're having to melt it by its heat of fusion. Well, you normally have to be removing heat from the absorber as it reacts with CO2, so that means we don't have to remove as much heat from the absorber, and correspondingly, over in the regeneration process, it's going from a liquid back to a solid, so you don't have to add as much heat in the regeneration process. All right? You guys with me? So just to emphasize, if we got something that's a reaction, delta H of reaction with CO2 of 50 kilojoules per mole, and we've got something whose delta H of fusion is 20 kilojoules per mole, that means instead of having to remove 50 kilojoules per mole in the absorber, I'm only having to remove 30. Now over here, instead of having to add 50 to make it unreact, I'm only having to add 30. Okay? So we decided we should do this, and so we had some ARPA-E funding for this. And it turned out that the best material is not technically an ionic liquid at all. People use a 100-degree melting point, has to be below 100 degrees to be called an ionic liquid. So our best material actually has a melting point, the pure material, of 166 degrees centigrade. This is a tetraethyl phosphonium benzimidazolide. 166 degree melting point. And so this is all of these are at 70 degrees centigrade. And so happy little solid here without any CO2 on it. we start adding very small partial pressures of CO2. So this is 60 millibar, and you can start to see it's starting to look a little bit wet. By 100 millibar, it's almost completely liquid, and certainly at 150 millibars of CO2, it's a complete free-flowing liquid. And this is all at 70 degrees centigrade. So the melting point of the complex is more than 100 degrees lower than the melting point of the original material. And so here are some uptake isotherms. I showed you the pictures at 70, but this is 60, 70, and 80 degrees centigrade. This is this tetraethyl phosphonium benzimidazolide. And so CO2 uptake is a function of partial pressure. And you'll notice we get very sharp uptake, and then it kind of levels off. All right? This material, the delta H of reaction is pretty much minus 52 kilojoules per mole, and that delta H of fusion is 19.9. All right, so consistent with the numbers that I showed you in the previous graph. So we wanted to understand these kind of sharp uptake isotherms, and so we looked at this as a eutectic, that we have a pure P-sil that has a melting point of 166 centigrade, and we've got the pure complex that has a lower melting point, and that we would be forming a eutectic of those two things. All right, of course, in equilibrium with CO2. So this is then a three-component, three-phase, one-reaction system. So that gives us 1 degree of freedom. So the thermodynamics tells us that for a particular isotherm at a particular temperature, we will have solid, liquid, and vapor in equilibrium at only one pressure. So that means that our isotherms shouldn't just be kind of sharp, they should be completely sharp. All right? So if I just look at this, so this is not exactly our material, but close. So if I just look at one temperature, this is 20 degrees, it says that I should have absolutely no CO2 uptake until I hit a critical pressure, in which case it should go all the way up to this critical capacity, all right? Totally vertical line, and then at any other pressures higher than that, it should look more like our Langmuirian sort of absorption. If I increase the temperature, it moves my critical pressure, where this happens, to a higher pressure, and the amount of uptake to a smaller number. So as I increase the temperature, I increase the pressure where it has the uptake and decreases the capacity. And this happens until I reach a critical temperature at which it starts going back the other way. And then eventually at a temperature as high as the melting point of the material, then it starts looking, it's just a Langmuirian thing like we saw before. So this says that we should actually have extremely sharp peaks, and that, of course, is a very good thing for a CO2 capture process, because you only have to make small changes in temperature or pressure to get huge changes in the capacity. So, we developed this material and worked with a company called Notre, who did the process modeling and the laboratory scale demonstration of it. We ended up having to make 8 kilograms of this material. I will never do that again. No, I will never. My postdoc will never do that again. So, all right. So this is a schematic of what they had. The way they designed it was actually to make it a slurry. So they used, because of the solid handling issue, and so they made it 1 part of the solid unreacted stuff with 2 parts of the reacted stuff. All right, and so they actually ran the absorber in a sieve tray column. So this is a normal distillation sieve tray column. You know, I was there, saw this working. It was really cool. I mean, there was this slurry went into the top, the CO2 nitrogen mixture was going in the bottom, and as it went down the downcomers, it became clearer and clearer and clearer until we had this beautiful clear liquid at the bottom. And then they ran a spray dryer system where you're not trying to completely desorb the CO2, right? You're only trying to desorb a third of the CO2 because only a third of the material is in order to make the slurry that goes back around. And so this is a schematic of their desorber unit. This is their costing. So they did not just energy costs, but full capital cost of doing this process. And so these are their final results. So compared to the aqueous amine, which would be 29% parasitic power, this comes out to be about 23% parasitic power, which corresponds to, when you put in the capital costs, it comes out to be about a 4.1 cents increase per kilowatt hour increase in the cost of electricity. So the points I would like to make is that these materials whose melting point when reacted with CO2 is much, much lower than the original material, it only happens some of the time. And my computational colleagues tried very hard to be able to predict melting points and were not real successful. So this was more from our intuition and understanding from the work that we had done. It's best if the melting point is high and the delta H of fusion is a big number. So that 20 kilojoules per mole was about as big as we could get. But that it does lead to an interesting process where we could potentially reduce both the energy and cost compared to aqueous amines. So for conclusion of my whole talk, I hope to have suggested that ionic liquids are very interesting tunable solvents with potential for many energy-related applications, with this CO2, post-combustion CO2 capture just being one of them. Specifically, we think being able to get one-to-one uptake is kind of a good improvement, as well as being able to understand and eliminate the viscosity increase upon reaction with CO2. We like that we can tune the enthalpy of reaction by putting electron donating and withdrawing groups on our anions, and that we can also tune the capacity not just with the delta H of reaction, but with the delta S of reaction. And then finally, this last work with these interesting materials that have this phase change property that we could potentially take advantage of. With that, that's kind of a photo of my group, and that's not what I was want to do. And I, of course, have to thank funding agencies. Most of this work has been funded by the Department of Energy, both through the National Energy Technology Laboratory and through 2 ARPA-E grants. I think I already mentioned my colleague, Bill Schneider, whose group does a lot of the DFT calculations that have been very helpful in our development of these materials, as well as Ed McGinn, who does molecular simulations, and Mark Stadher, who does work with the process simulations, trying to narrow in, and thermodynamic modeling, to narrow in on what are the properties of the materials that we actually want to help improve the entire process. And with that, I would like to thank you for your attention and be happy to answer any more questions.
How does sulfur fit in the picture? Since we're talking coal, you've already mentioned the sensitivity of the system to water. Thank you. Would there be sensitivities of the system to sulfur combustion products? And is this meant to be operated downstream of a flue gas desulfurization unit, or
right.
simultaneous with it?
Okay.
Or what?
So first off, physical solubility of SO2 in ionic liquids is extremely high. So if we could have used a ionic liquid that physically dissolves CO2, then we could simultaneously remove CO2 and SO2, because you'll notice these are really high mole fractions. Okay, but For the case, and I should also point out that H2S, we've actually done measurements of H2S in our laboratory after many safety reviews. And the solubility of H2S is also extremely high. So for pre-combustion, you could be removing both H2S and CO2. So that has potential. But for the post-combustion flue gas, where we've had to resort to the chemical complexation, the of the amines with the CO2, just like with regular molecular amines, SO2 reacts basically irreversibly with the amines and kills off your ionic liquid. So for the post-combustion case, this would have to definitely be done downstream of the flue gas desulfurization unit.
I didn't quite understand the cost statement you made. I assume that what you're talking about is just the cost of giving you carbon dioxide in a gaseous condition after you've taken it out of a mixture of nasty things. You have to do something with it at that point.
Right.
And that is probably the most expensive component of dealing with this gas, no?
No. So.
Or do I misunderstand? I can't read your multiple pie diagram.
Yeah, I know. All right. So, okay. So this is the standard way that DOE has you do costing for CO2 capture technologies.
But it's only capture you're talking
It's the
about.
capture part, but it includes the compression up to pipeline pressure. So that's the only way for it to be fair, because if you have different...
You haven't worried about where you put it. You've just got high-pressure carbon
Correct.
dioxide.
And so...
and you have to store it somewhere for 10 to the 5th
absolutely.
year.
Right. So you have to do transportation and storage after you do the capture.
How big is that component in general compared to what you're asking here?
What I have to rely on is the DOE reports.
Sure, I haven't read it.
Right. And the capture part of it is more than 90%.
It's more than 90%.
More than 90%.
Okay. So it'll put another few dollars there.
It would put another little bit on it. But the idea is that we really have to worry about the capture part, because it is really very expensive part. Not that the other is not important, because there's also risk mitigation issues with
But if it doubled
transportation
the
and
cost,
storage.
it would
But no, it
be more
wouldn't. Right.
problematic.
Right. But so this is a big part of the cost.
Thank you.
So at the risk of, since most power plants generate electricity, so at the risk of trying to make a perpetual motion machine, the other thing that people look to do with CO2 is to utilize it to make, for instance, liquid fuels. And there's been a lot of work with, you mentioned earlier, electrochemical reduction. How suitable are these particular phase change systems for electrochemical treatment?
I mean, this is a wonderful idea. And we've had some discussions with my colleague Prashant Kamat on conversion of CO2 when it's can we use the complexation, or can we design the complexation with the CO2 to make them readily activated to turn it into other things? And so we've started to have some discussions, and we haven't done any work on that. But that's a really, in my opinion, the only rational way of doing this is not, of course, electrochemically, but photochemically. So could we design an ionic liquid that would capture the CO2 and then help to activate the photochemical reduction of it to something else? So it's a wonderful idea. It's just not something that we've done enough work on.
The phase change behavior that you were showing with CO2 dissolution in the ionic liquid is really interesting. And I was wondering if you'd seen that same behavior with other dissolved components like lithium or sodium ions, that kind of thing.
So we've certainly seen the lowering of a melting point of an ionic liquid or an ionic solid, like these. But it's been simple when adding a lithium salt or a sodium salt. So I have one student who's been looking at solid-liquid equilibrium of these kind of mixtures, but it's all been, that we've observed, is simple eutectic behavior or formation of multiple complexes, but that can be explained by eutectic behavior. So it's the it's the physical thermodynamics that's happening that's making you get a melting point that's lower than the melting point of either of the two components, as opposed to this case where it's actually making a new species that has a lower melting point.
Thank you.
Any other questions? Yes.
Are there significant scale economies in applications to power plants, going from, say, 10 megawatts to 100 megawatts, 500 megawatts, and so on? How scale sensitive are the possibilities?
So, yeah, the question, I can repeat. So the question is, how sensitive are these materials to scaling issues? So designing it for, he started with a 10 megawatt power plant, and I would say starting it with a 0.1 kilowatt power plant, which is more like what their, their little columns are, to, larger and larger system. And, absolutely, because, and I am no expert in this, but we've measured kinetics, and the kinetics of the reactions with CO2 are very, intrinsic kinetics, are very fast, comparable with aqueous amines, right? So this is completely a mass transfer issue. So all of the mass transfer issues that you would have in scaling up from a small unit to a large unit are going to be tremendously important.
And then the last question by Professor Andlinger. Yeah.
Since we're talking about perpetual motion machines, the ability to uptake CO2 within an electrolyte and control the uptake with it would be, a potentially big boon to any kind of air battery, where instead of having a carbonate form, which is the real death sentence for anything you're exposing to a real system. So have you looked at these types of electrolytes with zinc or, God forbid, lithium as a way of handling and removing carbon dioxide, basically having an internal scrubber as opposed to an external scrubber, because that's one of the big, killers of any type of air battery.
Oh, I see what you're saying.
Yeah.
So put it in your air battery to scrub out the CO2 that's killing your...
While you're using it as an electrolyte.
Oh, no, I hadn't thought about that.
All right, well, we should talk about that.
Yeah. Good idea. Maybe.
So you spent a lot of time telling us about the effects of the CO2 on the viscosity of the system, because that's going to impact your process equipment and things. But you didn't mention anything about surface tension, the interfacial energy of these materials, which also has an equal impact. Is there any significant effects on, and what magnitude is the surface tension of these materials?
Okay, so we haven't done any surface tension measurements in my laboratory. Other people have measured surface tensions. You can help me if I got like 40, what are the units? Dynes per centimeter.
Yeah.
And
so that's less than water.
And so and they're all about, nobody's measured these, right? But of other common ionic liquids that they've measured, they're all about the same number. No one's measured it with the CO2 uptake. So that is a good question. So yeah, so maybe that's something else we should be measuring, is surface tension. Yeah.
Because that'll determine the size of the bubbles and things.
Oh, yep, that's right. Absolutely. Yeah. Okay.
Well, let's thank Professor Brennecke once more.
Thank you.